one of these many inputs. It will pass one of these many inputs to the output depending on the set of select lines. So basically, when we talk about the multiplexer, we can say that multiplexer or a data selector, or commonly abbreviated as MUX, is a combinational logic circuit which has group of data inputs, group of control inputs, and a single output. And control inputs are used to select one of the data input and connect it to the output. Control inputs are used to select one of the data inputs, and that selected data input will be given to the output. That's what the definition is given here. You can see there. Multiplexer means many into one. And multiplexer is also called as data selector, or commonly abbreviated as MUX, is a circuit with many inputs but only one output. And by applying the control signals, or which we call it as select lines, it can steer any of the input to the output. So here I have shown the general block diagram of the multiplexer. So what you can see in the general block diagram of the multiplexer? Yes?
N number of inputs and M number of selective lines.
Yeah, N number of inputs and M number of select lines. So in particular, it should have that N, normally we consider it as 2 to the power N, and M is nothing but the N, those many select lines should be there. That is, a 2 to the power N input and 1 output, if there are there, then that multiplexer should have N select lines. So instead of, we can modify it, instead of writing as N select lines, N data inputs, I can write 2 to the power N inputs, then N select line, and what? Single output. Such a combinational logic circuit is called as multiplexer, right? So we'll see how this multiplexer can be designed. The smallest of all the multiplexer is what? When N is equal to 1. When N is equal to 1, we get the smallest of all multiplexer. When you put N is equal to 1 here, how many inputs you will have then? If you take N is equal to 1, then we have 2 to the power 1 equal to 2 inputs. And how many select lines you should have?
One select line.
Only one select line, because N is equal to 1 you have taken. So one select line, 2 data inputs, and 1 output. That is the smallest of all multiplexer, and that smallest multiplexer is called as what? What it is called as? 2:1 multiplexer. Right. So what is the 2:1 multiplexer, and how that 2:1 multiplexer is designed? You can see here. I hope the block diagram is visible for you. This is the block diagram of what? This is the block diagram of what? 2:1 multiplexer. So when I say 2:1 multiplexer, how many inputs are there? 2 inputs.
2 inputs.
So I have shown here inputs as I0 and I1, and 1 output. 2:1. So 2 inputs, 1 output. So to select one among these 2 inputs, you need how many select lines?
One select.
Because you have to select one among these 2 inputs. So you need 1 select line. So how exactly this select line will steer one of these 2 inputs to the output? That is depending on the value of this. A can take values as either 0 or 1. Okay. So whenever A is 0, it will pass which input? This will be passed to the output. And whenever A is 1, what this will do? I1 will be passed to the output. So depending on the inputs, depending on the select lines, depending on the select lines, select line value, whether it is 0 or 1, one of the 2 inputs will be passed to the output. So either I0 will be passed to the output, or I1 will be passed to the output. So such a combinational logic circuit is called as 2:1 MUX. In brief, the explanation I have given here, you can read here. When the control input A is 0, the switch is in the upper position, and the MUX output Z will be equal to I0. When you will get Z is equal to I0? When A is equal to what? 0. Similarly, when A is 1, you get Z is equal to I1. So we can say that a mux acts like a switch that selects one of the data inputs, that is I0 or I1, and transmit it to the output depending on the control signal A. So how do you represent this multiplexer in a Boolean equation form is given here. Can anybody explain me how do you get this equation for this 2:1 mux? What is the equation I have written? The output Z is equal to A bar I0 plus A I1. So what information you will get from this logic equation? Yes?
So when like a bar will be 0, it the output will
That
it
means
should
not
pass
A
to I
bar,
naught.
actual variable is A. So this will be either 0 or 1, I said. Right? When A is 0, means obviously A bar will be what? 1. Is that clear? When A is 0, A bar will be 1, 1 and I0 will be I0. And obviously when A is 0, 0 and I1 will be 0. So 0 or I0, you are going to get what? I0. Is that clear? Right? When A is 0, A bar will be 1 and it gives you output as I0. Similarly, when A is 1, A bar will be 0. So this term will not be there. You will get A is 1, 1 and I1 as I0. So you will get Z as I0. When you will get Z as I0? When A is equal to 0,
0.
and you will get Z as what? I1 when A equal to 1.
1.
So depending on the value of A, you are getting output as either I0 or I1. Hence this particular equation represents what? What this equation represents? It represents the logic equation for what? For what? It represents logic equation for 2 is to
2 is
1
to 1
mux.
mux.
So I hope it is clear. What is 2 is to 1 mux? The smallest mux, how it can be designed. So this is the block diagram. This is the block diagram. This is the switch equivalent diagram. And this is the logic equation for the 2 is to 1 mux. Now, if you want to draw the logic diagram for this 2 is to 1 mux, how you can draw it? How do you draw the logic diagram for this 2 is to 1 mux? If you want to draw the logic diagram for 2 is to 1 mux, first you have to show how many inputs are there. How many inputs are there? 2.
2 inputs.
What are those? I0 and
I1.
I1. Sorry. I0 and I1. Fine. And then you have to get these terms. Like there is one more input, third input. What is that? What is the third input?
Selective
Select line A. 2 data inputs and 1 select line. Then to get the output Z, what you need to do is here you need to have one AND gate, you need to have another AND gate, then the output of these two AND gates should be given to what?
OR gate.
OR gate, like this, to get Z. Now what inputs you need to give? A bar you need. So what you have to do is this you need to give it to what? NOT gate, A bar and I0, and then A and I1. I hope the diagram is clear. Okay, anyhow, I am drawing it with the mouse. So it is not that, or you can say perfect, but you can get what exactly the logic diagram for 2 is to 1 mux is. I hope the diagram is clear. There are 2 data inputs, I0 and I1, and 1 select line A. So A bar I0 and A I1, these 2 terms you have to OR, because here there is a plus sign to get the Z. So depending on the value of A, now you are going to get the output Z as either I0 or I1. Hence this particular circuit is called as 2 is to 1 mux. I hope it is clear. What is 2 is to 1 mux? The smallest unit, smallest mux unit. All of you understood it? Any doubts here? Clear? Right. So if it is clear, we'll move further. So you can see here now, what is this mux now?
4:1 multiplex.
4:1 mux. So what are the parameters mux consists of? Yes. Richa, are you there?
Yes, sir.
Yeah. What exactly 4:1 mux consists of?
It consists of 4 inputs and 2 select lines and a single output.
Single output. So here the inputs are denoted by what? I have shown the 4 inputs. Data inputs. So what are the 4 data inputs we have shown?
D0, D1, D2, D3.
Okay. And what are the select lines?
A and B.
A and B. And the output is Y.
Y.
Now how one of these 4 inputs will be selected depending on the select lines? When I say there are 2 select lines, these 2 select lines will take how many values? Because in the previous case we have seen there was only one select line A. So how many values A has taken there?
1.
Two values.
2 values.
2 values, either 0 or 1. 1 among the 2 it will take. That's why you have selected 1 among the 2. Now you have taken 2 select lines, A and B together. So when you select A and B together, how many different values A and B can take?
4.
4. What are those?
0 0
0,
0
0,
1
1,
1
1,
0 1 1.
0, 1.
Yeah, 0 0 0 1 1 0 and 1 1. So there are 4 combinations of values of A and B, and depending on these 4 values, one of the 4 inputs will be passed to the output. So when A is 0 and B is 0, which input will be passed to the output?
D0.
D0. You can see here. For 0 0, D0 will be passed. For 0 1, D1 will be given to the output. For 1 0, D2 will be given to the output. And for 1 1, D3 will be given to the output. So when these two are 0 0, this will be passed. When 0 1, D1 will be passed. When 1 0, D2 will be given to the output. And when 1 1, D3 will be given to the output. That means at any given time, only one of the 4 inputs will be passed to the outputs depending on what? The select lines A and B. I hope it is clear. 4:1 mux. Now can anybody tell me what is the logic equation that can represent 4:1 mux? Right. So you have to use this particular table. This is not exactly a truth table we can call. We can call it like a function table of the 4:1 mux. Right. Using this table, can we write the expression for Y here? Because I have taken Y as the output. So for this Y output, what is the equation that we can write from this particular function table? Like how we have written in the previous case, A bar I naught plus A I1. Because there was only one select line, A. Now here we have 2 select lines. So depending on the values of A and B, you have to write. In fact, how this first combination of select line 0 0 is represented in terms of the inputs A and B?
A bar, B bar.
B
A
bar.
bar, B bar. Second one, how do you represent it?
A bar B.
A bar, B. Third one,
A B bar.
A, B bar.
A, B bar. And the last one,
A B.
A, B.
A, B. So depending on whenever this input combination occurs, you should get output D naught. So how do you write that first term in the equation for Y?
A bar B bar.
A bar B bar D naught.
A bar, B bar.
D naught.
Along with that, you should pass this output. Plus, next, how do you write it?
A bar B
A bar,
B1.
B1.
A bar, B, and D. Plus.
D1.
Plus what you write?
D1.
A B bar.
A,
B bar D2.
B bar, D2. Fine. Plus.
A
Last
B
one,
D
how do you write? A,
B D3.
B
B, and
D3.
D3. So you have 4 terms. So easily you can implement it using logic gates. How to implement it using logic gates now? How many inputs you have to show at the input side first? Yes, if you want to draw the logic diagram for this 4:1 mux, how many inputs you have to show at the input side?
4.
4 data inputs and 2 select lines. Totally
Select
6
lines.
inputs you have to show. Is that clear? 4 data inputs D0 to D3 and 2 select lines A and B. Then you have to get these combinations of AND operation using how many 3 input AND gates? Now you need 3 input AND gate because there are 3 terms in each of the product. So how many AND gates you need? 1, 2, 3, 4. So 4 AND gates you have to use 3 input, and output of all these 4 AND gates should be given to 1
OR gate.
which how many input OR gate?
4 input OR gate.
4 input OR gate. And definitely you can use the inverter wherever required to get the complement of the select lines. I hope that is clear. You can draw the logic diagram. Many a time they will ask, design 4:1 mux and draw the logic diagram using basic gate. Design means you should start with this block diagram first, then write the function table, then write the equation, and then that equation should be translated into logic diagram. I hope the designing is clear of 2:1 mux and 4:1 mux.
Yes. Yes, sir.
Yeah, like that. If they ask for 8:1 mux, how you can do that? 8:1 mux design. Suppose if I ask you to design a 8:1
3
mux.
select lines.
So how many select lines you will be showing?
3.
A, B,
3
C.
select
And how
lines.
many inputs?
8
8
inputs.
inputs.
8 inputs. You can represent those 8 inputs by what? D0 to D7 and the output Y. Then how do you modify this table for 8:1 mux? Instead of A and B, now we have to show A, B, C, 3 inputs. And how many values 3 inputs can take, or how many combinations you will get with 3 inputs?
8.
8 combinations. What are those 8 combinations? Starting from
0,
0
0,
0, 0,
0 0
0 till 1, 1,
1
1.
1
0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. These are the 8 different combinations you are going to get, and based on these combinations, one of the 8 inputs between D0 to D7 will be passed to the output. So you can easily write the equation again. So the equation will consist of now how many product terms? How many product terms you can get
4
in the equation?
product terms.
4
How many?
4
Not 4, 8 product term,
8.
and each product will have 4 what variables. Is that clear?
Yes.
You are going to get 8 product terms, but every product will have now 4 variables. Like here we have 3. In the previous we have only 2. Now in that you will be getting 4. Why 4? You will be getting terms, 3 select lines, and one of the input should be attached based on that combination of the input. And then easily you can implement that again using basic gate. The same process of designing is explained in more detail here for the same 4:1 mux, which I already discussed. Here the control inputs or the select lines. Again, you should remember sometimes they call it as control inputs or select lines. It is one and the same. And the actual input are called as data inputs. Here 2 select lines A and B are shown, and 4 inputs I0, I1, I2, I3 are given, and the output is Z. So you can see here A bar, B bar. There I have written D0. Here it is I0. Then A bar B I1 plus A B bar I2 plus A B and I3. Then you can have this 4:1 mux. This is the SOP equation, and easily we can draw the logic diagram. You can see here. This logic diagram is actually for the truth table which I have shown for this particular truth table. For this truth table, like this is the logic diagram. You can see 4 data inputs, D0, D1, D2, D3, then 2 control lines A and B. We have taken a complement of that wherever required. We have obtained these 4 product terms. Each product term is having 3 terms into it or 3 variables into it, and then these 4 outputs of the AND gates are given to one 4 input OR gate to implement Y. That is what is called as designing of 4:1 mux. I hope now it is perfectly clear for everyone. What is mux? How mux is designed, right? This is what 4:1 mux circuit. This diagram, everything is shown there. Equation, right? And one illustration also is shown. What happens when A0, B0? Which gate output will be high or low, and what is the final output that you are going to get? Everything is explained in this particular slide. So any doubts in this slide? Is it clear?
Yes, sir.
Yes, sir.
Like complete designing of a 4:1 mux with illustration is shown on this particular slide. Okay, shall we move ahead?
Yes, sir.
Right, this is what is explained. Then the commercial multiplexer, all these multiplexers which we are studying, they are available in the integrated circuit forms. And ICs come in integer power of 2. That is always the multiplexer which are available in the integrated circuit form, they are available either as 2:1 mux, 4:1 mux, 8:1 mux, 16:1 mux, 32:1, 64:1. Always they should be in the powers of 2. Right? Then in general, how do you represent the output of a mux in the equation form is shown here. In general, suppose a multiplexer with n control inputs can have 2 to the power n data inputs, obviously. Then the general equation for the output of the mux can be written as, can anybody try to explain how we can write this particular equation for the mux? Can anybody elaborate by taking some value for n, where mk is the mean term of the n control variables and ik is the corresponding data input. Already we have discussed mean terms, right? Mean terms are nothing but fundamental product terms, right? So mk means, suppose if you write k equal to 0, m naught that is the mean term, right? So what this particular equation represents, can anybody illustrate? You can take some value for n, right? Maybe you can take n equal to 2 or n equal to 4 and just try to illustrate what this equation means. How we can use this equation as a general output equation for any multiplexer having 2 to the power n data inputs and n select lines. Yes. Can anybody try? With n equal to 2, one person should try, and with n equal to 4, the other person should give me the answer. With n equal to 2, who will explain this? How this equation can be used to write the output equation for the multiplexer having 2 select line. When I say n equal to 2, that indicates those many select lines and 2 to the power 2 equal to 4 data inputs. Yes. Can anybody? Yes, Sahana, are you there? Sahana, you are there?
Yes, sir.
Yeah. Can you illustrate this particular equation by taking n equal to 2? Just you have to substitute n equal to 2. And try to write the output equation what you get. And check whether you will get the same for 4:1 mux equation or not. Can you give a try? You understood mux
Yes, sir.
concept or no?
Yes, sir, I understood.
Yeah. Then this equation you are not getting. How we can use this equation as a general equation for the mux output?
Sir, I'm trying.
Yes. You just try to write. All of you try to write in your book. If you take n equal to 2, what this equation modifies to? And then some of you can try with n equal to 4 also. When n is 2, means it is 4:1 mux. And when you take n equal to 4, means it is 16:1 mux. Okay, you can try for n equal to 2 and n equal to 3. Because 16 combination you have to write if you take n equal to 4. Here again I am repeating, n means number of select lines. Select lines can be an odd number, but data input should be compulsory powers of 2. That you should remember. Because we can have select line as 1, 2, 3, 4, any number. But data input should be 2 to the power of select lines. Yeah, anybody got the answer for n equal to 2? Just you have to expand this. Summation k equal to 0 to 2 to the power n minus 1. So if you take n equal to 2, k will vary from what? 0 to, yes?
3. 3.
Because
3.
n is 2, 2 to the power 2 is 4, 4 minus 1 is 3, k will vary from 0 to 3. That means you are going to get how many product terms? 0 to 3 means 4 product terms you are going to get. What are those 4 product terms? Substitute k equal to 0 first. When you substitute k equal to 0, it becomes what?
0 I
M naught I naught
not I not
plus
plus M1
second
I1.
one
M1
M1 I1
I1.
plus
M2
M2
I2
M2 I2 plus
M3
M3 I3.
I3.
But here, what is that MK? What do you mean by M0, M1, M2, M3? It depends on what select lines you have taken. Suppose if you have taken the 2 select lines as A and B, can anybody tell me what is the mean term M0 then?
M3 I3
No, M0. If you have taken select lines as A and B, capital A and B, now you have to write these mean terms in terms of A and B, right? What M0 represents? M0 is a product term, mean term.
0
A bar,
0.
B bar.
A bar, B bar, exactly right. Similarly, M1, what you can write?
A bar B.
A bar
A
B
bar, B. M2,
AB bar
AB.
A,
AB
B
bar.
bar, and M3,
AB
AB.
A, B. That's what the final equation you will be getting it as what? Z is equal to A bar, B bar, I naught plus A bar, B, I1 plus A, B bar, I2 plus A, B, I3. And that's what we have got from the function table also. So definitely we can say that this equation can be used as what? A general output equation for the mux. Only thing that we are writing this equation in terms of the mean terms, and you should know how to write those mean terms depending on what literals you have selected for your select lines. Is it clear? Sana, understood?
Yes, sir.
Okay, good. Right, I have shown one more example here. Just go through it. I need not explain anything here. What is this multiplexer?
8:1 also.
8:1. You can see what are the select line, data line, output. How do you get the logic equation? Sakshi, are you there? Sakshi, you are there or no? Yes, Prashant. Prashant, are you there? Aniket? Aniket, are you there?
He's absent, sir.
Aniket is absent. Okay, Sohan, can you explain me
Yes,
here
sir.
how many data inputs are there? How many select lines are there? What are those data inputs, select lines, and how we have got these output? So
There
again,
are
as it
8.
said, this is like min term M0. This is min term what?
M0.
M1. This is M2.
M2.
This is
M3.
M3. This is M4. This is M5. This is M6 and this is M7. If you want to write it in that general equation. So here select lines are ABC, output is Z, and the data inputs are what? I0 to I7. So when ABC all three are 0, I0 will be passed, and when ABC all three are 1, I7 will be passed to the output. At any given time, only one of the many inputs will be passed to the output. Hence, it is called as multiplexer or many to one. Clear? Yes. And this is the block, what you can say, logic diagram for that multiplexer. Whatever the 8:1 multiplexer we have designed here, its logic diagram is shown here. You can see. How many AND gates we have used here now?
8 AND gates.
So one thing you have to remember, how many inputs are there? Those many AND gates you have to use. Whenever you want to implement any multiplexer using logic gates, number of AND gates will be equal to number of inputs. And each of those inputs should be given as one input to these AND gates. And the other inputs to the AND gates will be the minterms or the select lines which you have used. And the output of all the AND gates should be given to one OR gate to get the final output. That is what is called as a multiplexer design. I hope it is clear, all of you. Right?
Yes.
Now, suppose if the OR gate in the figure, if you replace by NOR gate, then what happens? Then the 8 to 1 mux inverts the selected input. That means you will get the same selected input, but the output you will be getting in complemented form. Here, instead of this OR gate, if you put a NOR, what happens? It will select that particular input, but the output what you will be getting is what? The complement of the selected input. Is that clear? If you want to, sometimes you want to select a particular input, but you want that input to be complemented, then what you can do? Simply instead of OR, you can put the right. But in many of the practical applications, normally we add one more input to the multiplexer called enable input. So what is the significance of the enable input? Right. Suppose you have a mux and we try to add, say, take example of this 4:1 mux. Normally 4:1 mux, I said there are 4 inputs, 2 select line, 1 output. But such multiplexers normally will have one more additional input called enable. Can anybody tell me what is the significance of this enable input? We try to add one more input called enable, as the name itself indicates. This particular circuit will be enabled only when the signal is active. That means normally if enable is 1, then only it functions according to the select line and the data inputs. And if enable is 0, what happens? Even if you apply the data inputs and the control inputs, output will be what? 0. If enable is 0. That is what is the significance of enable signal. I hope it is clear. We use another type of multiplexers as an additional input called enable. So when enable signal is connected to the 5th input of each of the AND gates, when you add that enable signal, here you will get one more signal for each. Here you have to add one more for each of these AND gates, and that is enable. Now suppose if that enable is 0, what happens? As I said, one common signal you have to apply for all, and that is called as enable. If you make enable 0, irrespective of what is the data input or the control input you have given, what output you are going to get? Assuming it is OR gate only, not NOR. What you are going to get? What will be the output of all the AND gates?
0.
0. So what is the final output then? What is the final output? Output of all the AND gates are 0, and those zeros are given to OR gate. So obviously OR gate output also will be 0. That means when enable is 0, you are going to get output as 0. In that case, these will not have any effect. So these will come into effect only when this fellow allows. So the enable is like the controlling person. He will decide whether the mux should behave according to the data inputs and control inputs or not. If he is active, then only it will allow those inputs and control inputs to pass, and accordingly you should get the output. But if you say I am not allowing, that is if enable is 0, the output will become what? 0. I hope you understood the significance of enable. It is like one switch, though you have given the inputs, right? We can say that I'll give one simple example. Like you can take the fan itself. Normally fan will have a regulator, right? The regulator will have a different speed. By varying the knob of the regulator, we can control the speed of that particular fan. But this regulator will come into picture only when the main switch is on. So here you can relate that main switch like an enable. If it is on, then only your regulator will have an effect on the speed of the fan. But if you have turn off the main switch, and even if you are changing your regulator, you are keeping it at high speed, will the fan rotate? Yes?
No, sir.
No. So there we can say that that main power switch is like what? Just one simple example I have given you to illustrate the concept of enable. There the main power switch is acting like a enable. Like if power switch is on, then only your regulator will come into picture and accordingly the fan will behave. But if the main switch is off, then what? Even if you vary the speed from the regulator, that will not have any effect because the enable is not active. That is the significance of enable in the multiplexer. And this is what is shown. The different arrangements of the enable in the 4:1 mux are shown. In the first case, what is shown? In fact, A and B, like first, all four combinations are different. If you take the figure A, what is this? This particular mux is called as active high mux. Active high mux means what? Whenever enable is 1, then only it will be active, and based on the select line S0, S1, it will give output Z as one of the inputs I0 to I3. Right? So active high and active high enable and active high output you are getting in the circuit A or the arrangement A. What is this arrangement B? What type of enable you are using again?
Active high.
Active high. Then what is the difference between A and B here? Just now I have told you.
We have used NOR gate.
Yeah, NOR gate. That means the output is what? Active low. Whenever you see bubble at the output is active low output. And when there is no bubble, active high output. So the first case is active high enable, active high output. Whereas second arrangement is what? Active
Low enable.
Active high enable, active low output. Is that clear? Then what is the third one then?
Active low enable,
Active low enable and active high output. Whereas the last case,
active
Active
low
low
enable,
enable,
active
active
low
low enable, active low output. Now what do you mean by active low enable? Anyhow, I have told you active high output and active low output I have explained you. What is the meaning of active low enable?
Excuse me, sir.
Yes?
So in C, we are using active low enable, then output will be low, no?
No, that's what I am asking the question. Your doubt will be clear if someone gives me the answer for this question. I am asking one question. What do you mean by active low enable? If you get the answer for this question, automatically you will get the answer for your question. Can anybody help me? What is the meaning of active low enable? Or before that, active high enable means what? That means you have not understood active high enable also.
Active high enable means giving input as a 1.
Yeah, active high enable means whenever enable is 1, that time the circuit is active. Is that clear? And when active low enable means what? When E is 0, that time the circuit is active. Again, don't relate with that logic diagram with the AND gates. When you use AND gate, it is called as active high circuit. So if you want to implement active low enable, then you have to go for NAND gates. Is that clear? So active low enable means what? When E is 0, that time the mux is active, and depending on the select line, it will give you the output. Now can you tell me, if somebody has asked, who is that asked the question? Like when active low enable, the output should be low? May I know the name?
Akash.
Akash. Yes. Have you got your answer or no? Output will not change here. The way you are enabling is different. I'll give the same example now of your fan. Normally switch is on, right? When we consider it as logic 1. When switch is on, the fan will be on and you can control the speed using regulator. In active low logic, it should be opposite. Switch is on, but the on switch we are representing by 0 level. It is called as negative logic. Have you heard about the word positive logic and negative logic? Akash?
Sir, but E is 0, like the main switch will be off only, na sir?
No, that's what I am telling. This is the representation. Don't go with that. When it is 0 means only off and 1 means on. That is positive logic, normal logic. Yes, you are right. But there is one more logic called negative logic. In negative logic, what is done is 0 is considered as on and 1 is considered as off. You got my point, Sahil?
Yes, sir.
Positive logic means what? The normal logic. 0 is considered as off, 1 is considered as on.
On.
Whereas negative logic means what?
0 is
0 is considered as on, right?
Yes,
And
sir.
1 is considered as off.
Off.
I hope it is clear now.
Yes,
Active
sir.
high and active low,
Yes, sir.
right? So only thing, the way you are enabling is different. Rest all functionality remains same. Means if I give E is equal to 0, you have to design the circuit in such a way that when you receive E equal to 0, your circuit should be active. So it is up to you how you are going to design that circuit. Is that clear? And in the active high case, what has to happen? Whenever I give you E equal to 1, it should function normally. And whenever I give E equal to 0, it should give me output as 0. Whereas in active low case, if I give you E equal to 0, it should function normally. And when I give you E equal to 1, I should get output 0. Got the point? Got the difference? Akash, Sahil, so on, all of you?
Yes.
Yes, sir.
Anybody
Yes,
else
sir.
having any doubt? However silly doubt it is, you should get it clarified. Don't bother what the question I am asking is right or wrong. I hope all these four combinations are clear then.
Yes, sir.
Anybody is having any doubt still? Yes, Jyoti,
No, sir. Understood everything.
Akanksha,
Yes, sir.
clear?
Yes, sir.
Good. Right. Then the one more before I close for the day, the remaining thing we'll discuss it in the next class. One last thing is shown here. You can see like what type of multiplexer we have used here. What type of multiplexer is seen here
2
on
is
this
to
slide?
1.
2:1 mux. Now, what we have done here is we have constructed we have used 4 2:1 mux to select one of the two 4-bit data words. Because normally multiplexer, what it does, it will select one of the many inputs and it will give it to the output. But suppose I have a 4-bit data, right? I want to transfer one of the two 4-bit datas. Then how I should do it? Are you getting my question? If you use single 2:1 mux, what it does? What single 2:1 mux does? You have two single bit inputs, and based on the single select line, it will pass that one of the two single bit input to the output. That means output you will be getting single bit. But now I have two numbers. Say x0, x1, x2, x3 is one 4-bit number, and I have another 4-bit number y0, y1, y2, y3. Now what I want is, based on the select line A, when A is 0, I should get x0 to x3, that 4-bit data at the output. And when A is 1, I should get the 4-bit data represented by y0, y1, y2, y3 to go to output. So what you should do? As I said, single 2:1 mux gives you single bit output. Now you want 4-bit output. And since you want 4-bit output, what you need to do is you have to connect 4 2:1 mux cascade as shown there. You can see here, this is first 2:1 mux, second 2:1 mux, third 2:1 mux, fourth 2:1 mux. And for all these four, we have connected single mux control or the select line A. Right. Now you can see what are the data inputs given to the first mux: x0, y0, x1, y1, x2, y2, x3, y3. Every mux will have two inputs. That's what we have shown. And every mux will have one output: Z0, Z1, Z2, Z3. Right. Now, how this combination of four quadruple 2:1 mux structure works? Whenever A is 0, and that A you have given to all the mux. So, what input the first mux will select, second select, third select, and fourth will select? All of you get 0. Which input will be selected by each of the four muxes?
First input.
Yes,
X0, X1, X2, X3.
So what output you are going to get then at the 4 muxes? All 4 simultaneously you are triggering with the same select lines. So what is the output you are going to get? What will be Z0, Z1, Z2, Z3 here? Z0, Z1, Z2,
Zero.
Z3 will be equal to what? X0, X1, X2,
X1, X2,
X3. When A is 0.
0.
And when A is 1,
Y0, Y1, Y2, Y3.
Y2, Y3. So means what you are doing here? By using 4 2:1 muxes, at any given time, we are passing 4-bit input, one of the 2 4-bit inputs to the output, and that is what is shown in this case. You can see here, X is of 4-bit, right? Y is of 4-bit, Z is of 4-bit, but A is of what? A is what? Single bit only. So when A is 0, this 4-bit data will be transferred to output, and when A is 1, Y will be transferred to the output. So again, in effect, it is behaving like a 2:1 mux only, but every input is having multiple bits as the input. In particular, here we have 4 bits in each of the inputs, right? Okay, so that is about the multiplexer. The remaining part of the multiplexer, we'll study it in the next class. If you have any difficulties, any doubts, you can ask. Hope all of you understood the concept of multiplexer.